All right, now in this example, we're going to find a singular value decomposition of a 3 by 2 matrix. So the procedure is exactly the same as the earlier example we did. We're going to start off by computing A transpose A. Then we're going to find the eigenvalues and the eigenvectors for that matrix. So that's 1 negative 1, negative rad 2, 1 negative 1, times our A matrix, and when we multiply these out, the top entry we're going to get 4, then we're going to get 0 here, we'll get 0 here as well, and we get 4 here. So fortunately for us, we got lucky in this case, and the eigenvalues are immediate to read off. They're just both equal to 4. And so that then tells us the singular values of A are just the square roots . Okay, so they're both just equal to 2. They're both just equal to the square roots of those eigenvalues. Okay, this might be a good time to remind you, if you're enjoying the content, smash that like button, subscribe to get all the newest linear algebra content. Now at this point, we're going to then find the corresponding eigenvectors. So lucky for us, both our eigenvalues are the same, so we're just going to do this in one step. So lambda 1 equals lambda 2 equals 4. So we're going to take A transpose A, and we're going to subtract 4 times the identity. But subtracting 4 off the diagonal just gives us 0, 0. So if you haven't seen this before, this can be kind of confusing. You don't know what to do at this point. But really, because there's no pivots in this matrix, it means that both variables are free. So x and y are both free variables. So we can take our vector xy, and we can split it up and get one vector for each of our free variables. Okay, and now that we've done that, this gives us our v1 and v2. So v1 is equal to 1, 0, and v2 is equal to 0, 1. Now I want to point out we got lucky on a few sort of facts here. The first is that both of these vectors are already unit vectors, so we don't have to normalize. The second fact is that these are both orthogonal to each other. Now, because we started off, because A transpose A, which is where these eigenvectors came from, because it's a symmetric matrix, we're guaranteed to be able to find a basis of eigenvectors, an orthogonal basis of eigenvectors. And eigenvectors that come from different eigenvalues will be guaranteed to be orthogonal to each other. But if two eigenvectors come from the same eigenvalue, there's no guarantee that they have to be orthogonal. And therefore, you might have to do Gram-Schmidt to make those two eigenvectors orthogonal. Now, in this case, we got lucky, and they already happened to be orthogonal to each other, so we didn't have to do that. Okay, so we did get a little bit lucky here. So at this point, so far, we have enough information to construct sigma. So remember, sigma is a matrix that's the same shape as the original matrix, and we just plug in the singular values along the diagonal. And V is the matrix you get by plugging in the orthogonal or orthonormal eigenvectors that you just found for A transpose A. Now the last part is we want to find the columns of U. And again, to do that, we use this little formula. So U1 is equal to 1 over sigma 1 times AV1. So in this case, sigma 1 is 2. A is equal to 1, negative rad 2, 1, negative 1. And V1 is just 1, 0. So this just gives us 1/2 times 1, negative rad 2, 1, which ends up just being 1/2 negative rad 2 over 2, which is just negative 1 over rad 2, and 1/2. Oops. Okay, so this is our U1 vector. our u2 vector is solved for similarly. That's 1/2 times a times the v1 vector, which is just 0, 1 in this case. And so we get 1/2 times which should be negative 1/2, negative 1 over rad 2, and negative 1/2. Okay. Now, if you check the two vectors that we just found should be orthogonal to each other. Okay, and so you can check by taking the dot product of u1 and u2, and they should be orthogonal. They should also be unit vectors. Now, the problem is we don't have any more singular values or vectors to work with. We've sort of exhausted all of the singular or all of the vectors that we had to work with. And this happens when you're working with a matrix that's taller than it is wide. So if you're working with sort of a tall, skinny matrix, then you're going to run into this problem where you run out of vectors when you're trying to find your columns of U. So what you can do is you can say, well, let's now look for a third vector. Okay, and let's say that third vector is x, y, z. Okay, we don't know what it is yet, but we're going to try and find it. So we want to find a third vector that's orthogonal to the first two vectors we already have. So we want u3.u1 to be 0 and u3.u2 to be 0. Okay. Now when we do that, we can actually write out both of these facts gives us a linear equation. We can take the vector x, y, z, and we can dot it with u1 and set that equal to 0. That's going to give us one equation, and then likewise this is going to give us a second one. So let's go ahead and do that. So u3.u1 is xyz dot u1, and the u1 we had was 1/2. Sorry, that's not 1/2. 1/2 negative 1 over rad 2, 1/2. And so this gives us 1/2 x minus 1 over rad 2 y plus 1/2 z equals 0. And doing the same thing for u2, it's going to give us something very similar. So I'm just actually going to copy this down just to save a little bit of time, except it doesn't let me paste. That's weird. So it's negative 1/2, negative 1 over rad 2, and negative 1/2 again. So this gives us negative 1/2 x minus 1 over rad 2 y minus 1/2 z equals 0. Okay. And I can then essentially put this, I've got two equations, I can put this as a augmented matrix. And I don't like all these denominators. So I'm going to multiply everything by, say, 2. It's going to be 1, negative rad 2, 1, negative 1, negative rad 2, negative 1. And if I row reduce this, it just works out to 1, 0, 1, 0, 1, 0, 0, 0, which tells me that x is equal to negative z and y is equal to 0. So that tells me then that the vector I can take from my u3 vector is, well, let's just write this as the vector I'm looking for, remember, is xyz, and so I can plug in a negative z up there, a 0 for y, and a z down there. But of course I want to normalize. So I'm going to take that vector, that negative 1, 0, 1, I'm going to normalize it. It gives me negative 1 over, negative 1 over rad 2, 0, 1 over rad 2. And now that I've done this, I have enough information to build my U matrix. So I put U1 in first, followed by U2. And then I put my U3 in first, in last, sorry. Okay. And you can check, and these vectors should all be orthogonal to each other. They all should be unit vectors, and that completes the process. So the last thing to do then would just be to check that really A does equal U sigma V transpose. So we can do that computation here, and we see that we actually do get the correct answer in this case.